Hello everyone, welcome back. I hope you've had a nice break, the coffee break. Now we are in the session for the first grand challenge of MMSys 2021. Our grand challenge is called Detecting Cheapfakes, and I hope that you find it exciting and insightful. This is a grand challenge organized and sponsored by these four institutions you see, YouTube, and Google AI, Simula Metropolitan Center for Digital Engineering in Oslo, Norway, University of Bergen in Bergen, Norway, and the Technical University of Munich in Munich, Germany. These are the organizers. My name is Chisemi Dogu, and I'm coming here today from Oslo, Norway. I'm a researcher at Simula Research Laboratory in Oslo, and I will be joined by Shivangi Anihan, who's a researcher at the Technical University of Munich, Germany, and she will join us remotely. Let's start with what the challenge is and why we're having this challenge at all. Our challenge is titled Detecting Cheapfakes, but what exactly are cheapfakes? We have all, I think, heard about deepfakes, right? This is a relatively well-known concept, but what are cheapfakes? Cheapfakes are, well, quite literally the cheaper versions of fakes. You know, they're cheaper than deepfakes, which means, for instance, that you do not have to use AI or any kind of sophisticated algorithm or anything to produce them. And you would just rely on what we call cheap manipulations of multimedia content. Here I have a few examples. For instance, you can have an original photo, which you simply just Photoshop. Yeah, this is a cheap manipulation, and this would be like producing a cheap fake. Or you could have a video. I'm sorry about the pointer. You could have a video which you just cut and paste and patch, you know, in any way you like. You can speed it up or slow it down, and then just publish it. And then you would be manipulating the content in a way that actually did not cost you so much. Yeah, you could just be using non-AI operations. Or, which is the most interesting part for us now as the topic of our challenge, you could recontextualize stuff. What that would mean is that, for instance, you would take a piece of content, whether it be a text or multimedia or whatever, and you just use it out of context. You know how we do in arguments? Sometimes we say, you're plucking my words. You know, you're putting my stuff out of context. That's precisely what recontextualizing in the form of cheapfakes would be. You would take, for instance, an image, a news image, and then you would just pair it with some random caption. The problem is that, first of all, that these are super prevalent, you know, that because they're so easy to make, they're so cheap, everybody can do this. Everybody can play with content and manipulate content. And the second problem is that they might not actually be so random all the time. You know, when I say, for instance, you match some news image with a random caption, imagine someone malicious, a malicious person or a news outlet using clickbait type of captions on a news image that is really not just made for harmless fun purposes, but to manipulate people or for monetary gain or for political ideological purposes. Yeah. So the effects really can range from being super simple, harmless, to systematic misinformation campaigns like all of us have, I think, been subject to in the past few years. So what does our challenge do? When I say it focuses on recontextualization, what does our challenge or aim to do? We want to focus on detecting the misuse of photos, such as this, real photographs, with conflicting image captions in news items. Yeah? And the more technical way of defining this is we want to detect out-of-context tuples in news items based on a data set that we have provided. The tuples are one image and two captions. Here I have an example. I just wanted to show you like the range of it, or you know, the scale of the problem. I don't know if everybody's able to see it, but there's a black bus with Black Lives Matter banner on one of the sides of it. And this was simply, I think, Toronto Raptors, a sports team, rolling into the NBA bubble in their bus, which they just happened to have signed with Black Lives Matter. But, for instance, a news outlet could be presenting this as buses purchased by Black Lives Matter supporters to transfer members to riots. Yeah, so you see the kind of harmful and more systematic kind of manipulation I'm talking about here, and this is precisely why we care about the problem, to make a grand challenge out of it. Just as a summary of what we wanted from our challenge participants, we wanted them to look at this kind of tuples. We call them, let's say, 3 tuples, one image and 2 caption, and we wanted them to tell us whether it is not out of context, yeah, let's say 0, green, or out of context. And here you see some examples. Yeah, there could be a real photograph with 2 different yet truthful captions, which we asked our participants to rate as not out of context. And others where, for instance, one of the captions were false, not truthful, we wanted them to mark it as out of context. So this is the kind of detector we wanted people to program and deliver to us. What we did is give a data set from the Cosmos project, which Shivangi will tell you more about now. And this data set was, as I showed you earlier, full of tuples like this. Yeah, and they were asked, as I mentioned, to make a detector, and we evaluated essentially like a true-false kind of classification at the end. We have a challenge overview paper. I have the link here, but you can just check from the web page. I would like to invite now Shivangi to present to you the Cosmos project itself and the data set that we provided in a bit more detail.
Okay, so as already explained, this challenge is about detecting out of context images, and what it means is that images are legit, meaning that you don't change anything in the image, but what you do is you basically share this image in a false or misleading context. And for example, you have this image of Obama, and this is basically from year 2014, where he was visiting Maryland to discuss with scientists about Ebola vaccine. And this same image was recently shared with a caption that Obama is in Wuhan lab and he's discussing something about bad project. So this misuse, where you take the same image but share it with a false or misleading information, is the out of context use of images, and that's the crux of this competition, that the problem that we are targeting. And what we did is we basically started out by creating a data set where we gathered a bunch of images. So for every image, we collected some captions, and then we used reverse image search and found different captions for the same image. And this way we collected multiple captions per image. And finally, we collected captions on a wide variety of topics, from elections, environment, global warming, racism, especially the topics where there's more misinformation. And in the end, we provided a large data set with more than 100,000 images for training and validation, and a very tiny test set, which is basically gathered from fact-checking websites like Snopes, and on which we basically evaluate our results. And as a first step, what we did is we basically removed all the named entities from the captions to sort of like remove any bias from the models. Such as you see that there's this person's name, Robert, Grace, McGuire. We replace it with like the synonym person, and this is like a place, Granby, and we replace it with location. So this is just a text pre-processing that we apply to our captions. And then there are 2 things. So first, we have like a training scheme, and our training scheme is self-supervised because we don't have these out of context captions for all the images in our data set. So we're trying to learn it in a self-supervised fashion. And the way we do is like we collect a bunch of images, and then for each image we gather multiple captions. So for instance, this is like an image of a train accident, and this like one website shared this image with something about rescue workers, and the second website shared the same image with something about passenger train. And same like this image of scooter, and this was shared with these two different captions by different websites. And then what the idea is, basically, we want to have a positive association of the captions that are related to the image. For example, these top two captions, like rescue workers and the passenger train, are positively related to this image. And the bottom two captions, electric scooter and scooter, they are negatively related to this train accident image, but are positively related to this scooter image. And vice versa for the other captions from the data set. So this is like the main idea. And the way we do it is like we take the image, we take one associated caption, which is like the matching caption, and one random caption from the dataset, which we call non-matching caption. And then for this image, we basically first apply some object detection. And for this, we use mask-R CNN, and we detected the objects in this image, and then used a simple CNN to generate a fixed size vector for each of these objects. And in this case, we are basically producing a 300-dimensional vector. And same, we do it for these captions. So for each caption, we generate a single 300-dimensional vector. And then we basically do a dot product of these vectors for all of these objects with this caption to find which object in the image is the caption talking about. And yeah, and then we get some scores, and then we say that the score for the matching object has to be higher than the score for the random caption, and we train it with like a simple max margin loss. And once we are done with this training, we have some association of captions with the objects in the image. For instance, this is like the same image that I showed you before. So this is like an image of a train accident. And you see that the top caption, which talks about rescue workers, so rescue workers at the site of train accident, is basically giving a high score to this worker in the image. And the bottom caption, which says that the passenger train was stuck by a cargo container, is giving a high score to this train object in this image. Similarly, I have like another example where you get different scores for different objects in the image, and these are mostly genuine images in this slide. So for genuine images which are not misused, we get captions grounding with different objects. And secondly, if the captions are misused, so the false captions I'm showing here in red, it is always the case for the dataset that we collected that more or less they all ground with exactly the same object. So for example, in this left image, you see that the caption, the true caption says that this is like a photo of a soldier wearing exosuit, and this is like from a movie set. So this is talking about this person in this image. And then there's like a bottom caption which is like a false caption for this image, which says that a photo shows Russian soldier wearing exosuits. And this is also talking about this person. Similarly, for the other image, both of these captions are talking about this person standing in this image. So based on these kind of patterns in the data set, we came up with like a heuristic rule to do the classification for out of context and not out of context. And then once we had trained our model to generate the grounding scores, we basically take an image and two of its associated caption, pass it through our method, and then that tells us and gives us a binary classification label, whether it's out of context or not. And precisely what we do at test time, we basically take an image, detect all the objects in the image, take both the associated captions with this image, and one of them is true and one of them might be true and might be false. And then we pass it through our model, which we trained in the previous slide, and pick the most relevant object for each of these captions. So this bus is, let's say, the most relevant object for first caption, and this exactly the same bus is the most relevant object for the second caption, because in this case, both of these captions are talking about the same bus. And then we use an external language model, which we call sentence BERT. And we basically first compute similarity between these two captions. And we say if these two sentences mean completely different things, or they are semantically different and their similarity is lower than a certain threshold, but they align with same objects in the image. So they're saying different things, but they are saying different things about same object in the image. So that means this is an out of context. This is the misuse of images. But on the other hand, if we have captions talking about different objects in the image, then this is not always out of context, and this is mostly not out of context. So that's how we do our classification. And yeah, so that's like the Cosmos project, and this competition is based on this paper, which I've listed here. Now I'll hand it over to the winning team, who came up with a pretty good solution to improve the scores of this proposed method.
Thank you, Shivangi. Now I invite also Tankut Akgül to the stage. Tankut is one of the authors of this brilliant submission that we received called Cosmos on Steroids as cheap detector for cheapfakes based on the Cosmos model.
Thank you for the introduction, Cise. My name is Tankut Akgül. I'm an assistant professor at Istanbul Technical University, and this work was done in collaboration with Tuğçe Erkılıç Civelek, Deniz Uğur, and Professor Beğen. I'll skip these slides because Shivangi already explained very well what cheap, and also Cise also mentioned what cheap fakes mean. So I'm going to skip this slide. And also Cosmos was very well explained, and the stages, that the text processing, image text matching model, as well as the detection model, the heuristics that Shivangi mentioned. So I'm going to skip those as well. But maybe I can give an example to reinforce the knowledge about this Cosmos model. So we have a bridge-like structure here. And there are two captions talking about this bridge, and as you can see, the captions obviously mention the different things. Like one of the captions says this is a real bridge, and the other caption says it's a fake bridge. It's not a real structure. So the captions obviously don't have semantic similarity, so they are different. And since they both talk about the bridge itself, the Cosmos algorithm basically determines this sample to be out of context. But imagine one of the captions talked about the Eiffel Tower at the back, and it told something completely different from the other caption. Then in that case, these captions would be in context because they talk about different things in the image. So that's the main idea of Cosmos. And if you look at the mechanism that helps us determine whether a set of captions and an image is out of context or not, one of the things also Shivangi mentioned is the semantic similarity of the captions. So one thing you can immediately do is check the semantic similarity of the captions, and if they are not similar, you can say, aha, these captions are different. They talk about different things. So you can say, okay, this is out of context, but that's not enough. You also need to check the objects those captions are referring to. and that's why we are aligning the objects with the captions. But in the opposite case, when the captions are actually semantically similar, they convey the same message, then we can conclude that this sample is not out of context. I mean, Cosmos does that. But the problem with this is there's one shortcoming. The semantic similarity score that we obtain using this S-BERT model the Cosmos uses may actually give high similarity, even though the captions may have conflicting meanings. So that's one shortcoming that we have observed, especially looking at the test samples that Cosmos was failing. And the other shortcoming we have noticed is as Shivangi mentioned, the Cosmos methodology basically looks at the topmost object, the most aligning object with the captions given. But one caption may actually refer to multiple objects in an image. So let's say there's a plane with a engine in fire, and one caption may say this the plane with an engine fire crashed, and the other one may say it's landed safely. So the captions obviously convey different messages, but they talk about different things. Like one is like going through the algorithm, one caption may align better with the engine, and the other one may align with the plane. So Cosmos may conclude that these captions are not out of context, even though they obviously convey conflicting messages. So in short, we need to look at different objects that the captions may simultaneously refer to, not only the topmost object. And the last one is the threshold that's being used for object overlap. Like if you are looking at the most aligning object and comparing whether these objects the captions are referring to are the same object, there's an IOU threshold that Cosmos applies. It's an intersection of union threshold. And it uses 0.5 for this. And if this threshold is, if the overlap is more than 0.5, Cosmos thinks that it's, these objects are actually the same objects that the captions are referring to. But in the test set that we have observed and looking at the performance of the Cosmos, we have noticed that when the objects are actually separate, or the captions are referring to different objects in the image, the objects are actually completely separate. They don't have any overlap at all, or very little overlap. So their IOE scores are actually very, very small. So we can actually decrease this threshold much less than 0.5 to have a better detection or prediction performance. So we have come up, looking at these shortcomings, we have come up with 4 different methods. And these are differential sensing, fake or fact method, object-caption method, matching improvement, and IO threshold adjustment. So let's look at these one by one. So differential sensing is actually loosely inspired by the differential sensing in electronics. In RAM cell, for instance, you want to determine the charge level of a RAM cell. Instead of checking whether it's, let's say, has a voltage level bigger than 2.5 volts or less, just looking at an absolute threshold, you have 2 bit lines that are opposite charged, and you expose the RAM cell to these bit lines, and one bit line charges up, the other one discharges. By looking at the difference, the direction of changes of these charges, you can determine the charge level of the RAM cell. So inspired by this method, we actually come up with a similar method for detecting the semantic similarity. So we have 2 probes, just like the oppositely charged bit lines. One is the positive probe, and the other one is the negative probe. And the positive probe is generated, both of these probes are actually generated by one of the captions. And we add 2 phrases, was true and was not true, to end of this caption to generate these two probes. So for instance, the caption may say the picture shows there was an earthquake in some location. And the positive proof becomes the picture shows there was an earthquake in location was true. And the negative proof becomes the picture shows there was an earthquake in location was not true. So these proofs obviously convey conflicting messages. So they have opposite meanings. And then we basically check this similarity between these probes and the original captions. And if both of the captions align better with the positive probe, we determine that that these captions are actually have similar meanings, or they don't have a contradictory meaning. But if one of the captions aligns better with the positive probe, but the other caption aligns better with the negative probe, then we conclude that these captions actually have conflicting meanings. So that's the idea. So we check the relative scores, similarity scores between the captions, the original captions, and these positive and negative probes. And here's an example of that. We have this image that actually Cosmos fails to detect. And by using this method, we can determine, we can predict this caption correctly. So the sample to be correctly determined based on that. And the second one is the fake or fact method. This is actually a similar idea. We want to detect captions that have contradictory meaning. They convey different contradictory messages. And what we have observed is these captions usually include some offending words like fake, I don't know, disinformation, hoax kind of words. So a simple thing to do is just determine whether one of the captions actually includes one of these words and the other one doesn't. In order to determine that, we generate again a reference caption which includes all these words concatenated together or comma separated, and then check the semantic similarity, which is used, which is done by checking the cosine similarity of the embeddings that are given by the S-BERT model. And if one of the captions has high similarity, significantly higher similarity than the other caption, then we conclude that these captions are actually have contradictory meaning. So they are not, they may be out of context, basically. And this is one of the other examples that actually Cosmos misses. And you can see these captions, Cosmos thinks these captions are related. They are not out of context. They actually convey the same message. But if you look at the captions carefully, they are actually giving contradictory information. Like one says this purple lobster, and this is a genuine picture of lobster, purple lobster. The other one says this is not a genuine picture. So there's obviously a contradiction here. And the thing we check here, we catch is this not genuine phrase, basically, that word that we catch. And the next method is the Object-Caption Matching method. As I mentioned, the original Cosmos work only aligns the caption with the topmost object, only one object. But what we do is we check the highest n objects. In our work, we use 2, n as 2. But if the, let's say, top n objects scores, alignment scores are close to each other, they all together align well with the caption, then we combine the bounding boxes of those captions or those objects together to come up with a bigger region. And then compare the IOU threshold, the overlap of that bigger region instead of the original individual objects themselves. And here's an example of that. Cosmos originally thinks that this sample is actually out of context because the captions actually have contradicting or different, they are not similar, basically, semantically similar. and they talk about the same object in the image. That's the woman carrying that bag there. But the captions also mention about the town, the tank, other things in the picture as well. So if you combine the boxes, we come up with a bigger box. Now the IOU threshold or IOU score, the intersection of union score, becomes very low. In that case, we determine that even though Cosmos thinks that these captions are out of context, we determine that this sample is actually in context. And the last method is IO threshold adjustment. As I mentioned, the semantically dissimilar or not out of context captions typically refer to distinct objects in the image. So if the captions are semantically dissimilar, that's mainly because they talk about distinct objects in the image. And since they are distinct objects, the overlap score is very low. If you look at this plot here, the IOU value it shouldn't be threshold, actually, should be the overlap, the IOU itself. They are concentrated on the left-hand side, the blue dots on the left. Those are the samples that are actually not out of context. But since the threshold is 0.5, the purple samples are also considered as not out of context because they are below the threshold. So if we decrease the threshold to, let's say, 0.25, which we did, we halved the threshold value from 0.5 to 0.25, then these purple samples suddenly are considered or predicted as out of context correctly. But some samples may be missed, like these two blue dots. So these are the new samples that we correctly predict now because of the lower threshold. But these two samples now are missed. But as I mentioned, since most of the samples are still to the left of the curve or to this adjusted threshold line, we don't have many new false positives, which are these two samples that are newly missed. But they don't have, we don't have too many of them. And this is an example of this methods being applied. So there are two captions. They are talking about an iPhone, and the IOU threshold here is 0.33. So these captions are actually out of context. But since the overlap is less than 0.5, Cosmos thinks these actually are in context or not out of context. But if you lower the threshold to 0.25, then the overlap is obviously becomes over the threshold, which is 0.25. Then we can correctly predict that these captions are actually out of context. And here are the results. So the baseline is 81.9% is the Cosmos running on the test set given provided by this for this challenge. It's 1,000 samples in it. So we got 81.9% accuracy with baseline. If we apply differential sensing alone, we get a 3.7% improvement. Fake or fact, 3.0. And object matching, we didn't have too many samples that satisfied the conditions that I mentioned for catching these missed samples. So we didn't get too much improvement, but we wanted to get every bit of juice out of this improvement. So we wanted to add that, and the last one is this IO threshold adjustment. We get 1.7% improvement, and so the overall, if everything is applied, we get 6.4% improvement. And if you add up the numbers, obviously you should get more than 6.4 if you add them individually. So that means that there's some overlap between the methods. Some methods, like fake or fact, probably finds some samples that differential sensing also finds. So there are some common samples between those. Okay, and if you look at the performance metrics, you can see the numbers here. Since we didn't touch the model at all, like the trained model, we don't have too much latency added. We only do the similarity checking for the differential sensing method. We run, or a fake or fact as well, we run these captions through this SBIRD model to get the similarity scores. So we get 76.71 latency, millisecond latency per sample. And you can see the other metrics, we actually get pretty high numbers. And if you look at the model side, as I mentioned, we didn't add too much to the model itself. And one thing here is, like, we use SBIRD, and Cosmos uses SBIRD WK for the original semantic similarity checking. So we could actually use SBIRD instead of SBIRD WK. We could integrate SBIRD to the original Cosmos model as well. So use just one model instead of two different models. But we didn't do that because the SBIRD WK scores were already provided to us with the challenge. And if like, there are still some challenges ahead, considering this limited scope of cheapfake detection by using one image and two captions. There's still problems that we need to address, and I can give you an example of that here. So there's a fire in the picture, and then one of the captions says, like, this fire is in the city of Adana. It's a city in Turkey, and the other caption says there's a fire in the city of Antalya. So obviously these cities are completely different cities, and they both align with the picture. There's a fire, obviously. Even though there's fake information here, one of the captions is obviously fake, but I don't know which one. But and I cannot determine by just running this through the Cosmos, even with our improvements, determine that these captions are actually out of context. And the reason is, I don't know whether these cities are the same city or different cities, or like parts of the city. I don't know that. And especially since these cities actually are replaced by the hypernyms, by the named entity recognizer, I won't have those city names input to the model at all. So there's this shortcoming we need to address, maybe by using some extra information outside this model itself to detect cases like this. And that basically concludes my presentation, and thank you very much for your attention. If you have any questions, I'll be happy to answer. Thank you.
Thank you very much, Tankut. I think we have a question from the audience. You can directly use the microphone over there.
Hi, thank you. Thanks for the presentation. I had a question which was related exactly on your last slide. Indeed, I was wondering, well, you can detect that there is a conflict often between two tags, but indeed, I think it would be important to know which one is the correct one, or maybe they are both wrong, right? I think that's where still there is something to do. Do you have some ideas on how to address that?
You mean the fire example?
Yeah.
Okay, yeah. So yeah, we need to probably collect some information about the place here, for instance. Like, we need to have maybe a database to actually check whether these places, locations, are the same location or not. We cannot determine whether the captions are actually providing correct information. We can only determine whether they are contradicting or not using that. I don't know. Probably that's the best we can do. But if there are other things that we can relate to, like take a reference, like a fact-checking source, then we can compare this given information against that fact-checking resource or reference then maybe determine whether the captions are actually providing correct information or not. So we need an outside resource or outside information, extra information to be able to address that problem.
Yeah, but you are not working on that?
We are not working on that. Yeah.
Okay.
So this is the scope of this work. Like just given captions, 2 captions and 1 image, just determine whether the captions align. They all align together, or there's a misalignment among one of those those tuples, basically the elements in the tuple.
Yeah, thanks.
Yeah, sure.
Are there any other questions from the floor? We have one more. Please go ahead.
Hi, thank you for your talk. So I want to ask about the data set. Like, what is the constraint on the data set? Is it like it depends on, like if we feed your trained model a manipulated image with some captions, so will it be able to recognize something, or it will detect or produce wrong results? Like,
yeah, you have to have basically 1 image and 1 correct caption. You need to know that that caption is actually correct.
yeah.
And then another caption that's also related to that image. In that case, I can determine whether that caption is fake or not, that the second caption. Because I can check whether that caption conveys the same message as the other caption, and whether it aligns with that image as well. So I need to have a correct reference point, which is the first caption.
Yeah, so basically the assumption is that the input we are feeding to your model should be a correct image, and one of the captions should be correct, right?
Yes,
so this is the like a constraint to this problem.
Yes.
Okay, thank you.
Sure.
Do we have any other questions? I don't see any from the web. So we can thank Tankut. Thank you for the very nice presentation and also the submission. I can give a few updates now about our evaluation process. Very briefly. So as we've been talking about, we had made a data set of 1,000 images, or let's say these tuples, public, and the team, the Cosmos on Steroids team, used this public test set and which provided the results that Tankut presented here. What happened was we actually received 7 registrations, but only this team was able to finalize their submission and actually provide us with working code. I'm sorry, there's a typo over there, but the next thing we did was to prepare this hidden data set, this hidden test split, which is not 500 entities, but 700 entities. So we tested their model on a data set that they had actually not seen before. So those results Tankut presented were from the public, and we next did the hidden test split. And actually, it performed very, very well. You see here the performance of Cosmos on Steroids in terms of just accuracy here. 88%, this is what Tankut presented, 88% compared to the baseline model, which performs, which has 82% on the public. And on the hidden, it is, again, outperforming the Cosmos with 87%, where the Cosmos itself is 84%. So congratulations to this team. This is why they get an award. I would like to encourage everyone to also give them like a warm applause. I think Deniz, one of the authors, will be here during the demo session to show you their code in Colab, so that you don't need a Docker container and you can just see how it runs over the demo sessions. Thank you very much, everyone. This concludes this Grand Challenge session. Now we move on to the next Grand Challenge. Thank you very much.